Hi everyone, welcome to the second lecture of 572. So, in the previous lecture, we've discussed floating point numbers. We've got that out of the way. Now we're ready to move on to the more interesting topics related to neural networks. So the first step that we have to take is to learn how to numerically optimize a function, because that is one of the most important things that we will be needing when we train neural networks or any parametric model. So just like I said in the previous lecture, once we have a model that has a number of parameters and we want to fit it to our data, we want to obtain the best model that's possible. And in order to do that, we usually have to do some sort of optimization of cost or loss function with respect to the parameters that we have in our model. That's usually the procedure. Okay, so I think up to this point, you haven't yet done any optimization, any numerical optimization in your machine learning courses, right? So you just train machine learning models using the already built-in algorithms that are implemented in scikit-learn, or for linear regression, for example, you have analytical solutions, right? Okay, yeah, so this is the first time that we have to tackle the problem of optimization numerically. All right, let's get started. Okay, so if you remember, we also had 2 lectures dedicated to optimization in 512 in our algorithms course. And in that course, we only discussed, what did we discuss? What type of optimization did we discuss? Discrete optimization, right? So we had a bunch of separate states that we wanted to, and we wanted to find for which one of those states our loss function or cost function is a minimum or a maximum. For example, if you have a graph and you want to find the shortest path between point A and point B, then there are an innumerable number of paths that you can take from point A to point B, and then the goal was to find which path gives you the shortest distance. So the entire system, the entire number of paths that you could take was a finite number, right? So this was discrete optimization. And for discrete optimization, we discussed a couple of algorithms. Do you remember which ones were those? Exactly, linear programming, dynamic programming. Right. Here, we deal with a different class of problems called continuous optimization. And in this case, the function that we're trying to optimize can have infinitely many possible states. The other thing is that thanks to Newton and Leibniz, we have calculus that we can use in order to do the optimization, unlike the case of discrete optimization where we were relatively limited. Okay. Yes, that's right. So a type of linear programming is just continuous linear programming, but what we discussed was integer linear programming, and that's, again, a case of discrete optimization. The techniques overlap there for integer linear programming, but still it's considered discrete programming. You can't use the notion of gradients as we will discuss in this lecture. Okay. All right, so suppose that we have a function like this that we can see on the screen, fx equals to x minus 2 squared plus 5. And we want to find what is the minimum value for this function. Okay, so the typical approach that we have all learned in high school, or maybe the first math course that we have taken in school, was that we take the derivative and we set it equal to 0 because the extreme points happen where the derivative is equal to 0. And then we solve that equation for x to find where that particular case happens, and then that gives us the extremum point. So it's either a minimum or a maximum. Okay. All right. So something like this wasn't possible in discrete optimization. with derivatives, we take the derivative, we set it equal to 0, or we have some information about which direction to go to find the minimum or maximum. But in discrete optimization, there are just discrete states. We don't know if you move, there is no sense of direction, for one thing. So we don't know if we move to, for example, from state A to state B, maybe state B optimizes the cost function better. I mean, it gives a higher or lower value, but we don't know whether, what direction this is. That doesn't give us any information as to what other steps we have to take in state B. However, here, the situation is different. So we have a continuous function, we have access information to information from the derivatives. And that's a very useful thing to have. So that was the analytical approach, computing the derivative, set it equal to 0, find the maximum or the minimum. However, what's the problem with this approach? Yeah. So the thing is that the derivative becomes too complex most of the time. You have a number of various numbers of input value, features or input variables, or the function itself is quite complex. So even if you are able to compute the derivative, which is more straightforward than some other operations in calculus, compared to integration, for example, you probably can't compute the derivative, but setting it equal to 0 and find the root of that function can be really, really hard. Okay, so that's not the approach that we usually take when we want to optimize the cost or loss function in machine learning models. So let's see what are the tools available to us to tackle this problem. All right. So I'm assuming that you have discussed loss functions in 573, okay? And so we call this interchangeably the loss function or the cost function. In the context of this course, at least, these are the same things. Okay, so let's discuss the most famous cost function or loss function here, the mean squared error. So what this function does is that it basically computes the Euclidean distance between the predicted values and the actual data points that we have. So that's a measure of the deviation or the error that we have, and it squares that. And then it does that over all of the data points that we have. And then basically it takes the average of that value over all data points to obtain a measure of how much error we have, how much off we are. So that's the loss function. And the goal is to minimize this, because if we minimize the loss function, it means that the overall error has decreased. Okay, this is not the only loss function that we have. For different types of problems, we may use different types of loss functions. Can you name one other type of loss function that you have learned so far? Yes, binary cross entropy, for example, for classification problems. Okay. All right, so we start from a simple linear model, a very simple regression problem, and then we build our way towards more complex model in later lectures. But for this lecture, we'll only be working on this one and a case of logistic regression later on. Okay, so if we have a linear model, these are the parameters that we have. I don't know if it's too small or that's okay. Okay. Okay, so we have these three parameters, W0, W1, Yi, Xi, those are the data points. Okay, and we plug it into our loss function. So these are the predicted values, and this is the Y value from the data points that we have. And we square that, and then we take the average over all of the data points, and that constitutes our loss function. And the goal here is to minimize this function. Okay, any questions about the loss function here? Okay, let's move on. So I have a sample data set here from the Pokemon game, which Let me load the data sets. Okay, we have the name of the game characters and then their attack and defense powers, basically. Okay. And let's plot this data set. It can be any data set. This is just a little bit more maybe fun to work with. Okay, so a bunch of x values, a bunch of y values, and yeah, looks like a linear function. Okay, now the goal is to fit a line that minimizes the error for these data points. We have the model over here, and let's just assume that the parameters that we have, W0 and W1, are equal to 10 and 0.5, just as a guess. And let's see what that does. So here I'm just computing the values, the predicted values, using these weights or parameters that we have, multiply them by x, and you'll get the predicted values. Okay, so that's the fiddle line. But this fiddle line was, the intercept and the slope was based on a guess. So we can imagine that this doesn't really optimize the cost function, but it's a try. Okay. All right, now I have imported the mean squared error function from the scikit-learn package so as to compute this value over here. Instead of implementing it myself, we're just using that from scikit-learn. So let's see what's the mean squared error between the y, the data points, and the predicted values. So that's the mean squared error, 680. Okay. Now, just to simplify the problem a bit more, we're ignoring the intercept for now and just focus on optimizing the slope. So we're looking to find what is the slope that minimizes the cost function. That's the goal over here. Okay. All right, so here I'm just enumerating the values of the loss function for different values of the slope, right? So this is called a, what is this approach called? So I'm basically just listing all of the values in the range that I'm interested in. What's this approach? Yeah, it's brute force, it's grid search. So basically just look at all the values and find the minimum. Yeah, it's an approach. Okay, so if we follow the trend over here, you can see that the loss values decrease until somewhere around 0.95 for that W1, and then they increase again. So that's probably the minimum value for the loss function, and that corresponds to a W1 of 0.95. Okay. Oh yeah, that's 184. Sorry, I was Okay, yeah. So 0.90 here. Okay, that's one approach, not a very elegant one. All right, so what I have here, I have to zoom out a little bit. I have this interactive plot over here that can kind of show us what is how the mean squared error function or the loss function changes as I change the value of the slope. So here I have this slider over here that I can change, and as I change this, the value of the loss function changes, and you can see the corresponding changes in the fitted line. So as I move this over to this side, you can see, just like we saw in the output of the loss function, it kind of becomes a minimum around this 0.9. Okay, beyond that, the loss function here, the value increases, and also if I move it to the left, again, the loss function increases. And this is kind of the optimum point. Okay, questions about this? Okay. All right, so what is the problem with doing this grid search in general? Mm-hmm. And why? Mm-hmm, mm-hmm. Why is it computationally expensive?
Because you're iteratively checking things over and over and over again, checking all these things instead of just
Yeah. So, yeah.
And every single feature in your model has an associated slope, so it's times n features.
Exactly. So yeah, it is computationally very expensive because if you have, this is only for one feature or one input variable, But if you have several input features, several input variables, for example, if you have two input features, then instead of just checking a bunch of values in a column, you're going to have to check a matrix of values. So it's if you have n data points for each feature, you're going to have to check n squared values. And imagine what happens if you have 100 features. So grid search doesn't work, basically. Okay, so what did we do? What was the approach that we took in 512 when we said that we were optimizing? Well, we were working on optimizing problems. There was one key point in our optimization approach in that course. Pardon me?
Each decision wasn't a function of any other decisions.
That was for dynamic programming, but I mean, I don't blame you if you remember this, but this was kind of like at the center of what we learned. Usually when we had an approach that worked computationally better than another one, it was because that approach could eliminate a lot of possibilities that couldn't lead to the correct answer. So that this elimination of many possible ways that we could optimize our model in advance before looking at everything.
So if a sequential number is worse than the previous number, we can assume everything in that direction is probably wrong. So if you go up and the answer is worse, stop going up, eliminate that.
Yes, yes. So in this case, this is essentially what we do. So when we have multiple dimensions, instead of checking the entire domain and evaluating the function value for each combination of the input features, we take a more smart approach. So we use the information that's embedded in the derivatives of these functions, in the gradients of these functions, and we'll see how that works. So basically, that's the same as eliminating the possibilities that we know would not work. All right, let's see how that goes. All right, gradient descent with one parameter. So gradient descent is one optimization algorithm that can help us minimize our loss function. And the gradient is nothing but the collection of the derivatives of each function with respect to its input features. That's the so we might say derivative, we might say gradient. The gradient is the more general term. So if you have a function that's just f of x, then we say, okay, we take the derivative of f with respect to x. If f is a function of x and y and z, then we usually say we take the gradient of this function. So gradient means that take the derivative with respect to all of the variables of that function. That's the meaning of taking the gradients. Okay, so the gradient of a function, or if you're more comfortable with the word derivative, the derivative of a function tells us two things. The first thing is which direction to move so that our parameter decreases or increases the loss. You can say it works both ways. And how much our loss function, or any function in general, changes per unit change in its input features. Okay, that's a mouthful. So any questions about that? So it's very important to remember what's the meaning of a derivative of a gradient. Basically, the derivative gives you the rate of change of a function with respect to each unit change in the independent variable. That's the meaning of a derivative. It's kind of, if you take a function to be showing distance, and you take the derivative of distance with respect to time, that will give you velocity. Okay, so that's distance over units of time. Okay, kilometers per hour, miles per hour. That's kind of a derivative. Okay, so it basically gives you rate of change. Okay. All right, so to build up the intuition, if we are here, for example, if we are at this red dot, that point, then what the derivative gives me is that it tells me which direction to go in order to either decrease the value of the loss function or increase it, right? Because it gives me some value. It tells me that the derivative of this loss function with respect to the slope is, suppose that is positive or -1, okay? It means that if I change the slope, if I make a positive change in the slope, if I increase the slope, then the value of the loss function decreases by 1 unit in that direction. That's the meaning of the derivative, because it gives us the rate of change. Okay. All right, so we had our loss function, and now we can compute its derivative or gradient, and that's the derivative. So that's a quadratic function, and this is the derivative of that function. One very, very important thing here is that we're not taking the derivative with respect to x. Usually what we see in math textbooks is that we always take derivatives with respect to x. This is not the case here. Xi, yi, those are just constant numbers. We take the derivative with respect to the parameters that we have in our model so that we can find the parameter values that minimize the loss function. Okay. All right. Now that we have this, this gives us information about which direction to go so that we get closer and closer to the minimum value of a function. In this case, it's the loss function. All right, here I have created a function to compute the derivative for me, and then note that this dot mean means that I'm computing that value, this value, for each data point, and then I'm averaging that over the entire data set. Okay. So here, with a parameter value of 0.5, which is just an arbitrary value, the gradient in this is this value. Okay, what is the meaning of this? Yes? Precisely, yeah. So this tells me that for each unit positive change in W, if I increase W by 1 unit, the value of the loss function decreases by this amount. Why does it decrease? Because we have a negative sign there. Okay, so it means that it's getting smaller. And that's the rate of change of the loss function if I make a positive change in the direction of W. Yes?
Will the derivative of the loss function always be linear?
No. No, not necessarily.
And this relies on it being linear?
So here okay. No, I have computed the derivative analytically. I have computed it myself. So in this case, because of the way that the model, because of the assumption that I have with respect to the model, so the model is a linear model, you raise it to the second power here, and then you take the derivative, you come up with a function that's linear. That's just because we have this particular loss function in this particular model. In general, no, we can't say that. Yeah.
So,
Yes?
the amount of gradient changes once we're changing W. So,
Mm-hmm.
so this gradient is not constant, right?
Yes, that's right. Yeah. So generally, the gradient value is not constant. Okay, for example,
W value.
pardon me?
And depending to W value.
Yes, right. So for example, in what situation will the gradient be just constant? Exactly, if the loss function was linear. So in that case, you always have a constant slope everywhere. It doesn't depend on the value of the independent variable. Okay. But that's generally not the case. All right. Okay, now let's do some more plotting to see what's going on. Okay, this is my loss function, and this is the 0.5, the W equals 0.5, that point, and at that point I have computed the slope of the loss function. I have computed the derivative. Okay, that's the tangent line. And what it tells me is that at that point it tells me if you continue going in the direction of positive W, you'll be decreasing the value of the loss function. That's essentially what it's telling me, right? So I kind of always have to follow the direction of negative gradients, right? Okay, so that's what we'll be doing. So at this point, that's the derivative. It tells me it's a negative value, meaning that we are on the right path. If we continue going in the direction of positive w, we will continue decreasing the loss function. Okay, there's an assumption hidden in there. Yes?
You assume that you're going to a minimum?
Yes, and I also assume that this trend is going to be the same in the further steps that I'm going to take, because this can change. This only this definition actually only holds only for at the vicinity or neighborhood of this point. It doesn't mean that I'm going to decrease the loss function for the whole range of w's. So it's only correct at this point. It says that at this point, if you keep going, you're going to decrease the loss function. We don't know anything about other steps. Okay.
In terms of, you say like going, in terms of determining that, do you just test the value on either side? Is that kind of the approach there? Like, okay, so you have a number, negative 4,900, right?
Right.
That's a point. It doesn't tell you which direction to go. In that case, do you test then slope 5.1 and slope 0.49,
So-
and then see which one is closer to zero?
So it tells you which direction to go because the gradient has a sign, right? It's negative.
I mean, which direction to go in terms of W?
So you can go either in the positive direction or negative direction, right?
But how do you know which one to go without testing it?
It's the sign of the gradient because the derivative is telling me, okay, if you increase w, then the loss function is going to decrease.
Oh, yeah.
Right, yeah. Okay, other questions? Believe it or not, this is the most fundamental thing that you need to understand in order to be able to understand the optimization algorithms in even the most complicated machine learning models. This is it. Yeah.
So, again, by changing slope values, you're having different gradients. So, then, for example, if we start from like slope equal to 0.5, the gradient will change by like 5,000.
Right.
If we change the slope, or like if we change x.
If we change the slope. So we're working on w. Here, the independent variable is w.
Yes.
Okay, so if I keep, I'm basically looking for the value of w that minimizes the loss function, right?
Yes.
Okay, so because the gradient is negative, it's just telling me that keep increasing w. It's gonna decrease your loss function because the gradient is negative.
Oh,
Yeah, keep increasing. And we don't know what's gonna happen in the next steps. We will check at this point what is the value. Yeah, exactly. Yes.
Are we concerned about loss functions whose derivatives have multiple minima, or do you just not pick one more than a minimum?
We will get to that in a bit. Yeah. Okay, so how can we use this information? So I just verbally described what we should do in this case, how we can use that information to get closer and closer to the minimum value. But that's the formalization of that, this equation that you can see here. It says that in order to compute a new value for the w, which is the parameter, just take the old value and subtract the value of the gradient. Okay? And in that subtraction, you multiply it by a constant factor called learning rate. Okay, so you might have noticed that the value of the gradient is very large, and we might not be willing to take such a large step. Okay, so this is where this parameter comes in. This is a hyperparameter. I don't know if you've ever discussed this term. So it's a parameter that we have to set in advance. It's up to us to set. There's no way to obtain that value. Okay, so this is something that we have to decide. Okay, so we take the old value, and then based on the value of the gradient, we compute a new value for the parameter. Okay, and then we keep doing this until we reach a minimum. And let's see how that's done. Okay, so important terminology here. The alpha here is called the learning rate. All right, so basically, this thing that you can see over there, alpha multiplied by the gradient of f, that's the step size, right? That's deciding what is the size of the step in which that we want to use for changing the value of w. Okay, so here I have a code that implements this scheme. And I have inserted comments in the appropriate places just for you to see what's going on. But basically, the important part is here. It's just implementing what I just mentioned. So in the first step, I compute the gradient of the function. Compute the gradient of the loss function, okay? And that value of the gradient depends on the x's, on the y's, and on an initial value for the weight, because we have to start from somewhere, right? So we take a guess, start from some value of w, and then we compute the gradient. All right. Now we compute the step size. So the step size is decided by alpha, which is the learning rate. We have to set that in advance, and also by the gradient, right? Okay. And then finally, we just simply increment or decrement w by that step size. Questions? Yes.
So by setting lower values for hyperparameter alpha, probably model will take longer to run, and it's the case of
Exactly. So you take smaller and smaller steps, so it will take you longer to converge on the minimum value. Yes.
And in terms of like the trade-off, is it going to be the possible case of overfitting?
We will talk about that later on. Okay, questions about this scope. So this code. So the important part is these three lines. And I'm doing this iterative step until either the value of the step size becomes too small, or I have reached a maximum number of iterations. Because in case that I can't converge on a minimum, I don't want to go to infinity and do this over and over again. Okay, but this other condition is important. I'm going to continue doing this until the step size becomes very small, basically. Why is that? Exactly. So the step size becomes very small when the gradient becomes small, and when the gradient is small, it means that we're approaching zero, so we have approached a point in which the slope is zero, right? That's the minimum. Okay. Now, let's see a couple of visualizations and then discuss this further. Yeah, I forgot to run this. And then, all right. So this is, first I've just run the algorithm with these parameters. So I have started from an initial guess for the parameter, 0.5. This is just a guess. You can use other numbers. And then alpha, the learning rate. Again, this is something you have to decide. And then we have x's and y's of the data set. Okay? And then it starts iterating using that algorithm. So it starts from this value, computes the gradient, and then updates w, goes to the next step. Again, compute the gradient at the new step, update w. Do you still meet those conditions for the loop? If yes, then you just continue going, iterating and iterating and iterating until one of those conditions is no longer true. So usually the condition that becomes false is the one related to the step size, meaning that we have converged on a minimum. Because if the gradient is almost zero, it means that we are at the minimum. Okay. So you can see that after 51 iterations, we have found a value of w equal to 0.92, which is close to what we observed visually and using the enumeration. Okay. Now let's see how it looks like actually. All right. So this slider changes the number of iterations, so you can see what goes on for each iteration. So we start from a guess. This is the value of w, just a guess, initial guess, and then I start iterating. So first iteration, okay, I move in the direction of the gradient, direction of the negative gradient. Okay, next iteration, another one, more iteration, and then you can see that the progress slows down as I get closer and closer to the minimum value, right? That's because the value of the gradient itself becomes smaller. So we take smaller and smaller steps because alpha is constant. Okay. So All right, and you can see that it basically stops after iteration number 30. The gradient is super, super small. We're not observing any more changes in the value of the loss function. Yes? Yes, yes. In this case, we're just working on a simple case of having just one parameter because it's easier to visualize. Yes?
Is this function using a prepackaged one that we can use too, or is it like a custom function with plot gradient percent?
Oh, this is a function that we have developed, and I've put it into a separate code file that you can use. Yeah, so this thing plots gradient descent. This exists in a file called plot.py, and we have imported that at the top. But it only works for this very simple one parameter case. Yeah. Okay, other questions? All right. Okay, so now let's consider a number of different scenarios. So what happens if we increase the learning rate? So it means that basically we take larger and larger steps, right? Okay. All right, so after just 10 iterations instead of 51, we have converged on the minimum value of the loss function for this value of w. Okay, so just 10 iterations, that's much better, right? That's much faster. Okay, let's see how that looks. So iteration number 0, do this. Oh, very quick, right? Okay, yeah, that's much faster. So the algorithm is learning the optimal value of w much faster. That's why we call that a learning rate. Okay. All right, so since things are going well, why not increase it further? Oops. Okay. So this time, instead of, we had 10 iterations in the previous one, and we expected that if we increase that, we would probably have 2, 3 iterations, but that's not the case. If you increase it beyond that value, it actually takes more. Okay, you want to see why? Okay, it means that the step size is so large that it actually jumps over the minimum value. Look at that. So it still converges, but it jumps over the minimum value. So you cannot take very, very large learning rates. And why that happens is because if you imagine the tangent line here, that's the gradient. So there's the tangent line. Now, if I take a very large value of alpha, then the step size is too large. Then when I update the value of w, it actually increases the value of w beyond the minimum point. That's why we jump over the valley. Okay, there is also another case. So what happens if I even further increase the value of the learning rate? Let's see. Okay, so I've done this only for 10 iterations, and it doesn't seem like we're converging on a minimum. Let's see what's happening visually. All right. Okay. Yeah. Yeah. So we basically jumped too far, and at this point it just misses the minimum point, because at each step the gradient is getting larger and larger.
So what's causing the algorithm to stop at 10 iterations?
Oh, that's just the maximum value for iterations that we set. Yeah, yeah, because so that we don't have to loop for to infinity and the program terminates somewhere. Okay, so you can see that there's an optimum point for the learning rate. So we have to be careful in choosing that value, and we will discuss that in later lectures. All right. So I guess it's a good time to take a break. We'll be back in 3 to 4 minutes. All right, we're back. We are back. Okay, so we have just talked about cases where we have only one input feature. So basically, we have worked on a single variable optimization problem. However, in most models, we have more than one single variable. So let's see how that goes for the gradient descent algorithm with two parameters rather than just one. And as soon as you do it for two variables, then generalization to more is usually straightforward. Okay, so here I'm considering both the slope and the intercept, and in this case, the loss function is no longer a line in 2D, it's actually a three-dimensional surface. So here, what you can see is the loss function, and here on the x and y axis, you can see intercept and slope, W0 and W1. And this is a contour plot of the same function, looking from above and using the colors to show you the value of the loss function at each point. So for each W0 and W1, you'll get a value for the loss function. And that's what it's basically visualizing. This 3D plot also helps to see what it looks like in 3D. Okay, fancy stuff, huh? Okay. All right, so now the loss function takes this form. We have two parameters, okay? We have the predicted values minus the data set values. So take raise it to the second power and compute the average. Now, if we want to compute the gradient, this time the gradient has two components because you can take the derivative of the loss function both with respect to W0 and also with respect to W1. So in this case, you have two derivatives. And we call these two things together, we call it a gradient vector. Okay? It's a gradient vector containing all of the information about the derivatives of this function with respect to all of its independent variables. So in the first one, I'm taking the derivative of the loss function with respect to W0, and that's the derivative. In the second one, derivative of the loss function with respect to W1. You can see that they slightly differ. Okay.
Is the fact that x and then xi in it notational error, which is it? The
Oh,
equation,
that's right.
it's all of xi, right?
Yeah, that's right. So that should be xi because that's the data set points. Yeah. Okay. So now let's define this function that basically just computes these two derivatives for us. Okay. So it doesn't derive those things. It just implements these expressions in terms of Python. So let's just see what the value of the derivative is. So it says, okay, at this point in the loss function space for W0 equals to 10 and W1 equals to 0.5, this is the gradient vector. What does it mean? No.
So it's just two separate partial derivatives that are interpreted separately and all of the factors constant.
Okay. Yeah. We keep the fact. When we take the derivative with respect to one variable, we keep everything else constant, including the other variable. So everything constant. It means that this component means that if I keep everything else constant and only increase W0, this is the change in the loss function value. The other one, it means that if I change everything constant except for W1, then a positive change in W1 leads to this decrease in the loss function. Okay, so partial derivatives means that you keep everything constant except for the variable that you're working on, that you have taken the derivative with respect to. Okay? All right, yeah.
So the algorithm starts from the W that leads to kind of like a higher absolute grading value.
Okay, so we will get to that. Okay, yeah. So we have basically now acquired all of the information about the gradients of the loss function. Now let's see how we can use that information. So regarding that point, now how can we use it to actually change the value of the loss function or change or update the values of the W, it happens that the direction of the gradient, if you take it as a vector, the direction of the gradient shows you the direction of the steepest change in a function. Okay? So, because this is a vector, it's in a two-dimensional space, it's a vector. There are infinitely many directions that you can go. It's not like one dimension that you could either to the right or to the left, right? You can go anywhere you like. Okay, so in that case, you have to pick a direction. What is that direction? The steepest change happens in the direction of the gradient. Okay. All right, so we use that. We step in that direction in order to update the values of our parameters. So this function is very similar to what we had before. It's only different in the fact that W in this case, instead of being a scalar value, it's a vector, meaning that it contains two values, or it can contain more than two values. Okay, so we basically do the same thing. We compute the gradient, and then we multiply the gradient by a learning rate, alpha, and then we use that to update the value of W. Okay, so basically the same thing. And yeah, everything else here is about printing stuff and checking when we converge and stuff like that. And notice that here, instead of just checking the value of dW, I'm checking the sum of values inside that because it's not a scalar. I cannot check just the value of dW. I should compute some scalar based on that vector. Okay. So now let's run this, compute that. All right. It says that in iteration 43, we have computed this intercept and this slope. W0 and W1. Okay, let's take a look at that visually. All right, so this is a contour plot. This is W0, this is W1. This is the direction of the gradient, right? That's the direction in which the loss function changes the fastest, right? You can see that the loss function is changing. Because if you go in this direction, nothing changes. The colors stay the same, right? It means the values of the loss function stay the same, right? So I have to step in this direction, and that's the direction that the gradient automatically gives us. Okay. But can you see one problem with this plot? You can see that from this convergence history too. The value of the intercept doesn't change because the gradient is too small in that direction. Okay, it's not a problem if the gradient is just too small. The problem here is that we're implementing a numerical approach, and in this case, we want to converge in a finite time, in finite number of iterations. So in this case, this problem occurs because why does this problem occur? Exactly. So you can see the values for W0, 9, 10, 11. The values for W1, 1, 0.5. So the scales are vastly different. Okay. That's why when we compute the derivatives, the derivative of this in this direction becomes too small. The derivative of the other one becomes too big, and we basically don't see a change in the values of the intercept. Okay, that's why when we try to train machine learning models, we like to scale the variables, the input features, so that they're all on the same scale, because it introduces a lot of nice properties, one of which is this thing that you can see here. It improves the way that we can minimize the loss function. That's one thing. Okay. So let's see what the true values of W0 and W1 are. It's 14.0 and 0.75. And if you look at here, we're not that much off for the slope, but we're way off for the intercept. Okay, so the solution to this is to apply the standard scalar from scikit-learn. Do that, you already know this. And now, if you look at the loss surface, you can see that we're dealing with the same scales of changes in both directions. Yeah.
Just
With gradient boosting?
Any gradient-based tree.
Yes.
Even though trees in and of themselves are scale agnostic, for a gradient
That-
tree, you do scale.
That's right, yeah.
Without implementing this fix, wouldn't we expect that it would just be partial derivative part of the gradient would eventually get small enough that the intercept would be moved? Like it would just adjust the slope over and over again, which would make that partial derivative closer and closer to zero?
If we don't do the scale? Yeah. So essentially, we have to do a very large number of steps in order to get to that minimum. It eventually does that. Sometimes we have to be careful about something that we learned in the previous lecture. We might have some round-off errors because we're dealing with large numbers in that direction, and your changes might be too small. You get face the problem of the round-off errors, and you might not actually be able to converge on that. So that's one thing to watch out for as well. But yeah, always scale your input features, basically. That's the take-home message. Okay, now when we compute the gradients, you can see that they're more or less on the same scale. Okay. And now let's run the gradient descent algorithm again, and now we get reasonable values if we compare them to the actual values that come out of the linear regression model. Okay, so the linear regression model, we have an analytical solution for that one. You remember the normal equations and stuff like that? You invert that, okay. Yeah. So you can see that the solution that we have using an iterative algorithm is the same as the analytical solution. All right. And if I show you the convergence history visually, you can see that we have started over here, and then we nicely converged on the minimum for the loss function. And there's no problem of scaling anymore. Everything changes on the same scale. Okay. All right, now let's, just as an example, let's see how things change if we increase the learning rate. What do you expect if I change it too much? The bouncing back and forth, yeah. So this is what we see over here, but we're looking at it from the top. This is how it looks from the top, bouncing back and forth over the minimum value. Okay. Now, this is a visualization of the loss landscape for a real machine learning model, for a real neural network model. So the loss surface that I showed you here looks very nice and smooth. That's usually not the case in real neural network models. So you can see it's the valleys and ridges and a lot of local minima and global minima. So the actual loss surfaces are way more complex than the examples that I showed you. So it matters if we have algorithms that can handle these kinds of surfaces. So terminology, we call this a loss surface. We also can call it the loss landscape. It means we're looking at a visualization of the loss function as a function of its parameters. Note that this is not the actual loss surface. This is a projection of it, because in a neural network model, we may have millions of parameters, and we cannot visualize more than 3 dimensions. So this is just a projection. It's just projection on 2 parameters, yeah. Okay. So we have already discussed that we cannot, in complex models, we cannot simply take the derivative and equate that to 0 and then hope that we can find the minimum value using that, because there are usually no closed form solutions. And even if a closed form solution exists like the linear regression model, it might be computationally expensive to do that. So we are still interested in using iterative algorithms, even though, for example, in linear regression, we have an analytical solution, just because of the fact that inverting that large matrix may incur a lot of computational cost. Okay. Well, so we have learned about the gradient descent algorithm. It looks like a very nice algorithm, nice properties. However, you have seen that in order to compute the loss function, we have looked at the entire data set. So we had xi and yi, and we used to compute that value, average that over the entire data set. So this makes this gradient descent algorithm to be actually quite expensive to compute in real life situations. And this is why we use other variants of gradient descent, not the vanilla gradient descent that we have learned today. So we will discuss that in the next lecture. Yes?
I think we learned for the linear regression, we use those normal equations.
Yeah.
If we have issues with collinearity,
Mhm.
it becomes like the matrix near
Exactly.
Will gradient descent avoid that issue?
We don't have that problem. Yeah, because that happens because of you take the inverse and like stiff equations, stuff like that, but you don't have that issue with iterative algorithms. Yeah, the analytical solution is nice if you can compute it in reasonable time, reasonable resources, but otherwise the iterative just makes more sense. Yeah. Okay. So this is just the gradient descent algorithm is just one algorithm out of many. And you have access to many other different algorithms in the scipy.optimize package. And there is a function called minimize, which implements a lot of different sophisticated optimization algorithms, which we have over here. So here's our gradient descent algorithm, and these are the solutions that we got, W0, W1. Minimize takes as argument the function to minimize. It also takes the function's gradient and starting parameter values like the guesses that we had for W. For example, for the linear regression model over here, notice that this is a matrix notation. That's the transform of the vector over here. Okay, so this is the mean squared error in matrix form. And we use the matrix form because we no longer work with scalar parameter, because we have a bunch of parameters, not just one. So we have to use matrix computations in order to make things look nice and computationally tractable. Okay, so this @ sign that you can see, this is actually a matrix multiplication operator in NumPy. So it means that we have a matrix called X, which contains all of the values for the data points that we have in our data set. So each row is an observation, each column is a feature, that's X. Matrix multiplied by W, these are the parameters of my model, and then Y is also a matrix, a column matrix. Okay, and that's the way that we can compute the mean squared error. All right, so let's compute that. And now I just scale my matrices, and then here's the application of the minimize function from scipy, and this is the output. So you can see that the values that we get are actually the same or very close to the values that we get from our gradient descent algorithm. You also see a bunch of other outputs, for example, these values that I'm going to explain, and also some other messages at the top. Okay, so one important question. So we have a bunch of methods here. I can run through all of them and show you the values for W1, W0 that are computed with different methods. You can see the name of those methods over here. Okay, and each one gives us values close to ours, but slightly different. And I've told you that these are really nice methods, very sophisticated, can handle complex cases. So why are we focusing on gradient descent then? These methods also use gradients. No. The X is just a notation that SciPy uses to show you the function's independent variables. Yeah, it's just W's, yeah.
Why all these algorithms are using gradients?
Yeah, why instead of these, which happen to be better, why we're not using this and we're focusing on gradient descent this entire lecture? Pardon me? No, these are not, that much harder to understand. They have nice properties, but we could have definitely talked about those. The thing is, the gradient descent algorithm only uses the first order derivative, and it's called the first order method. Okay, And as I showed you in the plot, you have a tangent line and you base everything on that tangent line. However, you can actually make your approximation better, right? If you include higher order derivatives, you can actually, instead of fitting a line, you can fit a quadratic function. And that has nicer properties. You may be able to take larger steps and converge on the actual minimum much faster, right? But here's the thing. In order to do that, you have to compute the second order derivatives. And second order derivatives are okay as long as we are in just one dimension. But when you go to higher dimensions, that will be a mess. And it's computationally very, very expensive to do that. So if I let me show you this, this equation here. So basically what we do in this optimization algorithms is that we use okay, let me minimize this. All right. Okay, so basically what we do is that at each point of the loss function, we basically approximate that loss function with a line. And that's the first term in the Taylor series expansion. You can see that it says the value of the function in the point at the vicinity of this point is equal to the value itself plus the gradients that we have just learned about multiplied by the step size, the thing that we were working on, and then we stop there. With gradient descent, we stop there. However, you can increase the accuracy by including higher order terms, and you see that h of x. So that h of x contains all of the second order partial derivatives for the loss function. The first one, the nabla f, that's called the Jacobian and contains only information about first order derivatives, what we have been working on in this lecture. So Jacobian contains first order derivatives over here, nabla f, and the Hessian matrix, that's why it's called H, contains all of the second order derivatives. Okay, the Jacobian is fine. We can compute it reasonably well. However, the Hessian matrix is way too complex. If I actually show you, so it's a matrix like that, even for a scalar function that is basically a function of several variables. So it's way too complicated. Yes?
So it's every possible combination of variables, right?
Exactly. It's precisely.
X1 to the X1, X1 to the X1 to the X2.
Exactly. We have to compute all of the possible combinations of the partial derivatives with respect to all of the input variables. So that makes it really, really hard to compute these. These methods, to varying degrees, they actually compute the Hessian matrix. However, at the end of the day, some of them are more efficient, some of them are less efficient. However, they are always, almost always slower and harder to implement compared to a simple gradient descent algorithm. And that's why we don't use them. If you use these, you can actually see, okay, they converge much faster, especially in harder problems. However, their implementation is a mess. We can't really use them for neural networks.
Less steps, code more expensive steps.
Yes, yes. And the thing is, the rate of increasing in complexity is just exponential. Yeah, yes?
Right, so you're saying the generalization is for any neural networks or things that have larger number of parameters, it'll only use, or generally it's only use gradient descent.
Yes, 99% of the time we just use a variant of gradient descent called stochastic gradient descent, which we'll learn about in the next lecture, and that's usually it. Yeah, yeah. Okay, so now let's work on this lecture exercise, optimizing logistic regression. So basically working on a logistic regression problem and see how that works in the context of gradient descent. Okay, so let me show you this Pokemon data set again. And here we have taken 70 samples of legendary and non-legendary Pokemon characters, and we just want to classify based on the defense and based on the defense values. We want to see if we can predict if that character is legendary or not legendary. So basically, just a simple one-dimensional classification problem. Okay, this is just a plot of the data that we have. So these are the X values. This is the output. You can see that it's a logistic regression problem. Basically, we have two classes. One class is over here. The other class is over here. Okay, let's see how this works. So in logistic regression, what we have is a linear regression formula, and then we plug it into a sigmoid function to obtain probabilities. So basically very similar to linear regression. Okay, in order to write the linear regression equation in matrix form, this is what we do. So for the intercept, instead of having a value of x, we just have a column of ones, and we call that the trick of ones. I don't know if you've discussed that. Okay, awesome. So yeah, so we construct the matrix of the x values like that, and we also have the parameters of the problem, w0, w1. This is just basically, again, the matrix form of the equations that we had before. Okay, here is the Python version of it. W, an array, a column array, and then, a row array, and then x is a matrix. And then this notation is used to compute the multiplication of x by w. So if you do that, this is the result that we get, and this is showing you visually how these values are computed. So basically a simple matrix multiplication. 1 multiplied by 2, 5 multiplied by 3, sum up the results and put it in the y vector, and so on and so forth. So that's the matrix multiplication. Okay, and then once we are done with that, we just compute that value, those y values, which we call z here, and then pass it through a sigmoid function to obtain probabilities. Okay, so far so good. Nothing new. Here we define the sigmoid function as such, and we say that if we want a soft output, meaning that if you want the probabilities, we just return the value. If you want a hard output, meaning that if you want a label for the output, we set a threshold, and if it passes that threshold, we say it's belonging to class 1. If it doesn't, we say that it belongs to class 0. Simple as that. All right, now let's begin. So if we take the w to be 5 and 5, that's just a guess. We haven't optimized a loss function or anything. Let's see. Just want to show you a plot here. Okay, so this is how it looks like. So you can see that it's not working really well because it's just a guess. We have just used a guess for the values of w, and obviously we have to optimize it in order to obtain the most optimal model, basically. Okay, you can see that it's very bad actually. All right. So this is a function to compute the accuracy, and the accuracy is not much better than just a random choice of the classes, so 56%. All right. So I guess you have talked about this in other machine learning courses. We don't want to use the mean squared error loss function for classification problems, and that's because the MSE function, the loss function, does not have nice properties for basically implementing an optimization algorithm. And there is actually a plot here, I guess in the appendix, yeah, that shows you. Okay, so this is the output of the mean squared error loss for a classification problem. This is the output of the binary cross entropy. So you can say that this has a nice one global minimum. However, here if you implement a gradient descent algorithm, if you start from some place that's not the right place, then you might get stuck in local minima, and that's a problem we will discuss in later lectures. So basically we don't want to use minimum squared error. We use the binary cross entropy loss, which looks like this. Okay, now we have to take this loss and then compute its derivative, and I have the solution as to how to compute the derivatives in this appendix B. If you're interested, you can check that out, but you don't have to. So suppose that we have already obtained the derivative, and then we just put it into Python function form. Okay, and notice that we have these matrix multiplications over here because we're no longer dealing with scalar values. Okay, so this is just a Python translation of these two equations above. Okay, now I can use the minimize function from SciPy, and I'm passing the logistic loss into this. I'm passing a guess for the values of W, and then I'm also passing the logistic loss gradients, or the derivatives that we have computed. And notice that the parameter is called JSE Jack. It's Jacobian, the first order derivatives. Okay, let's run that. These are the optimum values for W such that the loss function is minimized. And just want to show you what it looks like. Okay, now it looks much nicer. You can see kind of that these values are packed here, and we classify that as class 0, and we classify the other ones as class 1. So this is the optimized version. So basically, you have seen that we have taken the same steps. We have the loss function, we compute the gradients, we pass it through an optimization algorithm to compute the optimal values for W. Okay, and now compute the accuracy, and it's 80%, not bad. All right, and this is checking against the score that we can obtain using scikit-learn. And okay, so this was for the case when we have only one input feature, the defense, but since we have already implemented things in matrix form, we can use any number of features that we like. So basically it works in the same way. So for example here, I use 2 features in this case, or maybe more. Defense, attack, speed, and 3 features actually. These 3 columns are my features, and this is my output. And this is just to show you that it works in the same way. You don't have to worry too much about the code. Okay, and these are the optimized values for the W's. So again, this is just to show you that the process is basically the same, regardless of whether you have 1 parameter or 100 parameters. It doesn't change anything. We are in matrix form. Matrix operations work the same way for 100 variables or for 2 variables. There's no difference. All right. So questions about this logistic regression kind of exercise? Again, this was merely to show you that the process is the same. Whether it's a different model, it's logistic regression, so okay, you use a different model, a different loss function, the process is the same. All right. So, we are almost done. In this lecture, we have talked about different optimization algorithms briefly, and then we focused on the gradient descent algorithm in detail. And then I showed you that we can use these algorithms to find the parameters that minimize the loss function, and that's their significance. We also briefly discussed why we're using gradient descent rather than more accurate models. And then, and we discussed that the gradient descent, as you can see, is relatively easy to code and relatively cheap to compute, and that's why we stick to gradient descent for neural network models. In the next lecture, we will learn about another algorithm, a variant of this one, called stochastic gradient descent, which is computationally much cheaper than even this vanilla gradient descent. And then later on, in lecture 4, we will start working with neural networks, because we will have all the pieces and bits. All right, that's it, everyone. Thank you so much, and see you next week.